Section 9. Okay, we've talked about the ideas of statistics estimating parameters. We've talked about the idea of a statistic being a random variable, which means that you do a sample, you pick the things that you're going to look at randomly, and in some way or another you get a number from them. And like any random variable, it has a pattern to its randomness, the probability distribution of the statistic, and it has a mean and a standard deviation. It has a center to its randomness and a spread to its randomness. We talked about how this played out in Section 8 for the situation where every individual you pick is a yes or a no. Now we want to look at the other type of statistic that we briefly overviewed in Section 7, which is the average of the numbers in the sample. So, in other words, Section 8 is the categorical situation. Every individual you pick or could pick is a yes or a no, one of these or one of those, one of these or not one of these. In Section 9, every individual you pick is a number, and there's lots of things we can do with numbers. We talked about them in Section 2, but the simplest is we can average them. We can take the mean of the numbers from the sample. The average of the rolls of the dice that you do, the average height of the people that you actually measure, and so on and so on and so on. Average spin of the spinner. And the first thing you notice is that people's heights and what can come up when you roll a die and what can come up when you spin a spinner have in and of themselves very different types of rules, right? So let's start there. Take a simple random sample of size n from any population of numbers with mean, mu, and standard deviation sigma. Let's think about how that plays out. You can be talking about, now we are talking about numbers. We're picking numbers from all the numbers that are out there. And we're picking n of those numbers. And as always, the populations are much larger than what we're actually picking. So it can be picking some people from the world vis-a-vis their heights from the heights of everybody in the world, 1,000 out of billions. Or it can be the population of all possible rolls of the dice. All possible rolls of the die, 1 or 2 or 3 or 4 or 5 or 6, all equally likely. Or it can be the all possible spins of the spinner, and so forth and so on and so on. So the first thing you've got to understand is that populations have a shape, a center, and a spread. If you're talking about the population of all possible die rolls, then you're talking about 6 bars, right? If it's a fair die, 1, height of 6th, 2, height of 6th, 3, height of 6th, 4, height of 6th, 5, height of 6th, 6, height of 6th, that rectangular 6 bars pattern. If you're talking about all possible spins of the spinner, then again it's rectangular, like we talked about in early Section 3, but now it's not individual bars, right? It can literally be any number. The example we did was pick a random real number from 0 to 4, uniform. So it can be 0 point anything, or 1 point anything, or 2 point anything, or 3 point anything. Very different type of variable, of course. The 1 is a discrete random variable, 1 or 2 or 3 or 4 or 5 or 6. The other is a continuous random variable, any real dot between 0 and 4. As for heights of people in the world, well, for all practical intents and purposes, it's continuous, right? For all practical intents and purposes, when you pick a height of somebody in the world, you can get any height between the shortest person in the world and the tallest person in the world. Now, if you want to be technical about it, you can only get, 7 billion different numbers, and that's assuming there's no repeats, that nobody in the world is the exact same height. So yeah, technically it is a discrete random variable, but you'd never think of it that way, right? You'd never list off all possible heights of everybody in the world and their probabilities. For all practical intents and purposes, it's close enough to true to say that they could be any height between the shortest person in the world and the tallest person in the world. So if x is the number you get when you pick from the population, or if you like, how the population spreads itself out. Remember, they mean the same thing. You can think of the 1, 2, 3, 4, 5, 6, all height 1/6 for the dice as being how all possible die rolls break down, or you can think of it as being the probability rules for what the next roll is likely to be. As always with probability, the one is exactly what we mean by the other. In other words, everything about the population, shape, center, and spread, carries directly over to the probability rules when you pick one. If x is the number you get when you pick from the population, then its probability rules are a complete reflection, are just an alternate way of looking at the shape of everything out there, right? We've talked about that since the beginning. 6 bars, all equally spaced, all the same height, is how all rolls of the die break down, or it's the probability rules for what the die is likely to be. Let's say nice, somewhat normal shaped, at least unimodal symmetric is how everybody's heights play out in the world, or it's the probability rules, which you're likely to get when you pick somebody's height, and so on and so on. If you can think of that rectangular continuous distribution, the uniform one from section 3, as representing all possible spins of the spinner, or you can think of it as what the spin you're about to do is likely to be, right? Our spinner from 0 to 4, well, half the spins are less than 2. There's a 1/2 chance the next spin is less than 2, and so on and so on. The one is exactly what we mean by the other. Take something right-skewed, right-skewed continuous, like, let's say, picking an income from somebody in the world, or the incomes of everybody out there that you have to pick from, right? So, as always, the one is exactly what we mean by the other. If that right-skewed shape can be the incomes of everybody in the world, or it can be the probability rules for the income you're about to pick. As always, the one is exactly what you mean by the other. When you pick once from any population, whether there's only 6 numbers that you can get, or whether there's an infinite number of different numbers you can get, or anything in between, when you pick once, the probability rules for x, that is to say, its probability distribution, and everything you can say about it, is a direct reflection of what's going on out there in the population. In other words, the shape of the population is the shape of the probability distribution for what you get when you pick. The mean of the population, average height of everybody in the world is 5.6, let's say, feet, is the mean of the random variable. When you pick somebody, they're bouncing around 5.6 feet in terms of what you're likely to get. Standard deviation of the heights of everybody in the world, whatever it is, let's say 0.2 of a foot. Well, then it's also the spread of what you're likely to get when you pick somebody from the world. And that's true for any random variable, right? In case of the die rolls, you can think of the 3.5 as the average of all possible die rolls, or you can think of it as the center of the randomness for what you're likely to get when you roll the die. The answer you get is bouncing around 3.5. You can think of the 1.708 as the standard deviation of all possible die rolls, or you can think of it as the spread of the random variable. What you're likely to get is bouncing around 3.5, and you'll probably be 1.7-ish to either side. This just goes back to section 5, the alternate ways of thinking about the mean mu in the first place, right? So the broader picture here is that everything you say about the population, shape of the population, center of the population mu, spread of the population sigma, carries directly over to the random variable x, what you get when you pick one. The shape of his randomness, the logical center of his randomness, that is, the mean of the random variable. The spread of his randomness, that is to say, the standard deviation of the random variable. This random variable has a mean, a center of its randomness, and a standard deviation, a spread of its randomness. And they are a direct carryover from what you had in the first place. This is just what probability is, right? Everything you can say about pick one from the population is just a mirror image of what's going on in the population itself. So remember that. Now, whether the population is all possible rolls of the die or 7 billion people, taking one away from the population, put it back, don't put it back, leaves no kind of hole whatsoever, right? So, effectively, everything we just said is true the second time you pick, the third time you pick, the fourth time you pick, the nth time you pick. Again, if your sample is size 100, then taking 99 die rolls from the population of all possible die rolls is taking away nothing. And taking 99 people away from 7 billion people is taking away essentially nothing, right? So, as always, samples don't compare in size to populations. They're not even close. So effectively, we have n independent random variables. That is to say, the exact same probability rules apply for x2, x3, x4. Well, of course, let x1 represent what you happen to get the first time you pick from that population. First roll of the die, height of the first person you pick. And let x2 represent what you're going to get when you pick the second person, or the second thing picked from the population, whether it's the second roll of the die or the second height of the second person you measure, and so forth and so on. Now, capital X, they are all in our future. So properly stated, it would say something like what the first roll of the die will be, what the second roll of the die will be, what the last roll of the die will be. The height of the first person you're going to pick, the height of the second person you're going to pick, the height of the last person you're going to pick. If they're still in the future, then the results are still random. The point is, going in, haven't done them yet, going in, they obey the exact same probability rules. We talked about this before in section 6 at the end, right? We had our two examples. On the one hand, first roll of the die, second roll of the die. They obey the exact same probability rules, and they don't affect one another. And we contrasted that with our number of heads, number of tails example, where individually they obey the exact same probability rules, but one utterly determines the other, right? We're talking about the former. We're talking about what they call independent but identically distributed. The technical term here is IID for short. In other words, going in, what x1 is going to be, what x2 is going to be, what x3 is going to be, what xn is going to be. Going in, they obey exactly the same probability rules. And individually, each and every one of them, probability rules, is a mirror image of what's going on in the population. Coming out, of course, they can be different things. But going in, what the first roll of the die is likely to be, what the second roll of the die is likely to be, what the last roll of the die is likely to be, well, individually, they're all that chart. 1, 2, 3, 4, 5, 6, all of height of 6, and so forth, right? If this is what the heights of everybody in the world look like, then this is the probability rules for the first person you pick, and it's the probability rules for the second person you pick, and it's the probability rules for the 100th person you pick. Going in, they're all pretty much identical. They obey the exact same rules, they have the exact same mean, which is the one from the population, and they have the exact same standard deviation, which is the one from the population. Individually, what x1 is going to be, everything you can say about its randomness, shape, center, and spread, are a direct reflection of the population. And what x2 is going to be is also a mirror image of the population, its shape, center, spread, and so on and so on and so on. So individually, they all obey the exact same probability rules, and those probability rules are just everything you had to say about what you're picking from in the first place. With all that in mind, let's hit you with some notation. So x2 is what the second number you pick happens to be, and so forth and so on and so on. Each of these is a random variable. They are alike in obeying the same probability rules, but they're independent. The second roll of the die has no bearing. The second roll of the die is not affected by the first roll of the die, and so on and so on. The height of the second person you pick is not affected by the height of the first person you pick. Even if you pick the shortest person in the world or the tallest person in the world and put them to one side, you've taken away essentially nothing, right? You haven't really changed what's out there. So they obey the same probability rules, but they're independent, because they obey the same rules regardless of what has come up before. So now some notation. Each one of these, thought of individually in his own right, is a random variable. And it has a mean, it has a shape, which is the shape of the population, and it has a mean, and it has a standard deviation. So the notations here will get a little bit hairy, and I don't think I've explicitly written them down here. But mu of this guy is just the original mu. And sigma of this guy is just the original sigma. What is mu of the first roll of the die? It's what, in probability terms, the first roll of the die is bouncing around. Well, it's that same 3.5, which was the average of all possible rolls. How far away from 3.5 is that first roll of the die likely to be? Standard deviation. Well, it's that same 1.7, which was how they were all spread out in the first place. And so on and so on. The same is true for x2, the same is true for x3, the same is true for xn. Every single one of these, x1, x2, x3, x4, x5, x6, they all have the mean that you had in the first place and the standard deviation you had in the first place. If you were talking about picking from a population where the average height was 5.6 and the standard deviation was, say, 0.2 of a foot, then the height of the first person in probability terms is bouncing around 5.6 and tends to be about 0.2 away. And the height of the seventh person you pick is bouncing around 5.6 and tends to be about 0.2 away, and so on and so on and so on. If the population is much larger than the sample, let's say some books will say 10 times bigger, some books will say 20 times bigger, 10%, 5%. But in any case, populations are much larger than the sample in the real world. We've beaten that to death. Then these are effectively independent random variables, and each has the same distribution as the population, same shape, same center, same spread. But we've already seen that that's not true when we go to combine them, right? The first roll of the die can be one of 6 numbers, nice rectangle. The second roll of the die can be one of 6 numbers, nice rectangle. But if you sum or average, it's just a unit change, divide by 2 or don't. If you sum or average 2 rolls of the die, then you get this pyramid-shaped thing with 11 bars, right? Centered at 3.5 if you average, or 7 if you sum. In other words, it's a different shape. So when we begin, let's say, averaging, when we begin averaging repeats together, as we've pointed out in the past, you don't get the same shape you started with. Now, the exception, remember, was the normal distribution. If you add 2 normal distributions, you get another normal distribution, and so forth. But even so, it changed the standard deviation. And if you're adding, it changed the mean. Another example, one spin of the spinner. First spin of the spinner, rectangular, 0 to 4. Second spin of the spinner, also rectangular, 0 to 4. But I forget whether in the problems it was sum or average, but again, it doesn't make a lot of difference. It was average. If we average 2 spins of the spinner from wherever to whatever, then it's a triangle, an isosceles triangle above that interval. Note the similarity there. In each case, when we average 2 repeats together, we get a new shape. But more than that, something where the probability is gravitating inward. Rectangle to triangle, rectangle to pyramid. See what happens? The probability, the area, same thing, gravitates inward. Now that changes the shape, of course. So when you combine, whether it's by addition or whether it's by averaging, we're going to be talking about averaging, but dividing by 2 or whatever, or not, is just a unit change. So when you average together independent repeat performances of the same variable, it is going to change the shape. And logically, because it changes the shape, it is at least going to change the spread, right? It is going to change how far stuff is from other stuff. If you're contorting the shape, then of course you're changing your average distance from the center. You're changing how far stuff is from other stuff. And if, as we've begun to see, the probability is gravitating inward, when you combine more and more repeat performances, then the spread is going to be going down, right? If the area probability is gravitating inward, then it's getting less and less spread out. I'll give you some pictures. All of this is by way of saying the following. If you do n random things and average them together, the result is a random thing, right? The average height of 8 people, the average height of 8 randomly picked people is you do something random and you get a number. It is a random variable. The average of 2 or 3 spins of the spinner, of 5 or 6 rolls of the dice, well, you do something random and you get a number. So the sample mean, the average of the numbers you randomly got, or randomly you're going to get, is a random variable. And like any random variable, it has a shape to its randomness, and a center to its randomness, its mean, and a spread to its randomness, its standard deviation. Now again, when you're talking about capital, you're talking about the future, right? The average of the 10 rolls of the die you're about to do, the average of the so many spins of the spinner you're about to do, the average height of the 100 people that you're going to pick out, and so forth and so on. It's in the future, it's still random. We don't know what we're going to get. The average of the n numbers you're going to pick, what it happens to be, is a random variable. It is another example of a random variable. The average of the n numbers you happen to get, or you will happen to get, sample mean, is a random variable with its own mean and its own standard deviation. And this goes right back to our rules in section 6. We're all set up now to talk about what happens when you add, subtract two random variables. Where would that be? Here, I guess. There they are. So we're talking about rules 3 and 4 here. When you add two random variables, you add their mean. And of course, y, it could be something plus something else, so this iterates, right? If you add or subtract so many random variables, you, well, in our case, you add their means. Standard deviation, as you can see, is going to be a little trickier, but this one also iterates. If you think about I'm not going to get into it, but if you think about how the algebra plays out for this, it doesn't matter how many you're adding or subtracting. You square them, add them, and take the square root. It doesn't matter how many of them you're adding. The principle will be the same. If you use it inside of itself, if y is something plus something, then you can check it out in your own spare time, but that's the way the rule will work. Regardless of how many pieces you're adding or subtracting here, you're going to square them, add them, and take the square root. Still 2 power and 2 root, but adding however many you need to add. So with all that in mind, oh, and by the way, we can also use the m here, right? That is to say, dividing by how many you did is the same, call it n, is the same as multiplying by 1 over n. And multiplying by 1 over n has the obvious effect on the mean. In our case, there would be no b, it would be 0. But multiplying the variable by 1 over n, which is the same as dividing by n, will have the obvious effect on the mean. Multiplication and division have the obvious effect on the mean, and they have the obvious effect on standard deviation. There's no b in our case. But if you multiply everybody by 1 over n, then you're going to multiply the standard deviation by 1 over n. Likewise. Remember, multiply divide is the easy thing. It's the shift, it's the b that's a little weird. So with all that in mind, there's going to be no surprises whatsoever for mean. You can do it in stages if you like. You can first talk about this random variable and then multiply it by 1 over n. But the bottom line is if you add so many, let's zoom in a bit. If you add so many random variables, then the rule from section 6 tells you that you add their means, right? And I just got done telling you that every one of their means is the original mean of the population, what we're calling plain old mu. So mu sub x1 is plain old original mu. Mu sub x2 is plain old original mu, and so forth and so on. For the dice, these are all 3.5. For the spin of the spinner, they're all 0 to 4. They're all 2. For the people whose average height was 5.6, they're all 5.6, and so forth and so on. And then again, to go from sum to average, we'll just multiply by 1 over n, right? And multiplying by 1 over n also has the obvious effect. You just do it. So the mean of x bar is that. Now, there's a word for multiplying. There's a word for adding mu to itself n times, and that's n times mu, right? So the bottom line is that the n's cancel, and we get the original mu. The notations are a living hell, but in the end, we're saying something very intuitive. The mean of the mean is the mean. The logical center, let's blow this up a bit. The mean, one more time. The mean of the mean is, last time I promise, the mean of the mean is the mean. The logical center of the average of what you actually pick is the center of what you're picking from in the first place. The average of so many rolls of the die is bouncing around in terms of what it's likely to be. The average of so many rolls of the die is bouncing around that original 3.5. The average of so many people's heights is bouncing around that original 5.6. The average of so many spins of our 0 to 4 spinner is bouncing around that original 2, and so forth and so on. As far as that goes, I think means are typically pretty intuitive, so that's not really any major surprise. Individually, each of these is bouncing around that original center of the population. The average of so many repeats is also bouncing around, that is the logical center of its randomness, is bouncing around the original, is the original center of the population. But as we've already seen, generally, when you're talking about things of this nature in this course, the mean formulas work out pretty much exactly the way you would expect, and there's always something a little weird about standard deviations, right? And there it is. You can't add well, we're not talking about subtraction here. You can't add standard deviations of random variables. You've got to square them, add them, and take the square root. And like I just said, that's going to be the formula regardless of how many you've got. So if you add several variables together, then the standard deviation is going to be square them, add however many you got, take the square root. It is still power 2 and root 2, but you add however many you got. So let's do the same thing for standard deviation. The standard deviation of x bar, the spread of the sample means randomness, the average of 100 rolls of the die, how likely it is to be different from the next average of 100 rolls of the die, and so forth and so on. The average of 5 spins of the spinner, how likely it is to be different from another average of 5 spins of the spinner. The average of 50 people's heights, how likely it is to be different from the next average of 50 people's heights, and so on and so on. The spread of the sample means randomness. The variability in what the sample mean is likely to be from sample to sample to sample. That's what sigma of x bar is. We've already seen that you can't add or subtract. This one you may want to do in stages. So first of all, we'll talk about adding them. Well, again, you can't add standard deviations. What you've got to do is square them, add them, and take the square root. But we've already established that every single one of these variables, x1, x2, x3, x4, x5, here it is, has standard deviation original sigma. 1.708 for the die, whatever I said, 0.2 for the people's heights, and so on and so on and so on. So each of them is that original sigma. Square them, add them, take the square root. And that is the standard deviation of this character. But then again, dividing by n, that is multiplying by 1 over n, has the obvious effect on standard deviation. That was the easy formula. Our m in this case is just 1 over n. So we'll do that. And there you go. That is the standard deviation of x bar. That is the thing that measures how one average of so many varies from the next average of so many, and so on and so on and so on. Now again, there's a word for adding this thing to itself n times, and it's n times that thing, right? Now dividing by n is the same as dividing by the square root of n squared, right? And then because of the way, because of the algebra of radicals, this is the same as radical of top divided by radical of bottom is the same as radical of top over bottom. And then look what happens. One of the n's cancels, but the other one is still with us. And then we can go back the other way. Square root of top, square root of bottom. Square root of bottom is square root of n. Square root of him squared is just him. So instead of going away, the n goes to the bottom. Does all of this, by the way, sound a little bit familiar? The algebra, we didn't do the algebra out, but I did it verbally. It is exactly the same thing that happened with the p-hat formula in the previous section. The exact same type of algebra. Dividing by n is the same as dividing by the square root of n squared and all that. The n goes to the bottom rather than disappearing. So it's pretty much exactly the same thing we did with section 8 in that regard. We end in the same place. The standard deviation of the practical useful statistic has an n in the bottom. So we'll talk about that in a second. Where do we stand? The sample mean, the average of the ones that you're going to pick out, the average of the n randomly picked numbers. The logical center of its randomness is the center of what you're picking from in the first place. If the average height of everybody in the world is 5.6 feet, pick out a few people and measure their heights. Pick out a few people and average their heights. What you're likely to get is bouncing around that original 5.6 feet. Average together so many rolls of a fair die. What you're likely to get is bouncing around that original 3.5, the logical center of its randomness. But as for the spread of its randomness, well, let's put it this way. Two things affect the average of 100 people's heights. Well, try again. Yes, two things affect the average of 100 people's heights. Two things affect how the average of 100 people's heights varies. Two things affect how one average of 100 people's heights is likely to be very different from the next average of 100 people's heights, and so on and so on. One example of an x-bar, another example of an x-bar. As always, this tells you how one example of it varies from the next example. So two things affect how the average of 100 people's heights vary. The fact that there is 100 of them, not 200, not 50, and the fact that we're talking about people's heights, not buildings' heights, not distances between galaxies, not heights of ants, not heights of trees, right? This has got to do with the inherent variation in what you're picking from. People's heights don't vary in the same way that tree heights vary, in the same way that building heights vary, and so forth and so on and so on. But also, unlike the above, unlike the mean formula, how many of them you're averaging together with the square root factors, how many of them you're averaging together is going to affect your answer as well. So let's study these two formulas. Note what number one is saying. Remember, in the real world, when we throw this into reverse, the average height of the people you measure is your estimate, your approximator of the average height of everybody out there. So if mu is the average height of everybody out there, and x bar is the average height of the 100 people you measure, then remember, this is our statistic, and this is our parameter. The logical center of the statistics randomness is what you were aiming for in the first place. Formula 1 is saying there is no bias. Again, a simple random sample eliminates the possibility of bias, and there it is in mathematical form. If you have a simple random sample, then our algebra leads us to the conclusion that we are bouncing around in probability terms the proper place. What does Formula 2 say? Well, notice what happens. Again, exactly as with the p-hat formula. Didn't work with the counts because obviously the different things you can get when you count the number of heads on 5 flips of a coin versus 5,000 flips of a coin. Obviously, there's more spread on 5,000 flips of a coin than 5 flips of a coin. You've got to divide by the total to make these things comparable. So it was never going to work for the count formula, but it did work for the p-hat formula, and here we're seeing a very similar effect. The average of so many things picked from the population. Well, there is the thing that measures its spread. There is the thing that measures how the average of 100 rolls of the die is likely to be different from the next average of 100 rolls of the die. How the average height of 50 people is likely to be different from the next average height of 50 people, and so on and so on. In other words, the variability of the statistic, how spread out you are from sample to sample to sample. And again, notice what happens. Exactly as with the p-hat formula, you've got an n in the denominator. So the larger the sample, the more you're dividing by. There is the square root effect, so it takes a little longer than you might think. But obviously, if the sample is 4, then you're dividing by 2. And if the sample is 10,000, then you're dividing by 100, which is more, and so on and so on. So it takes a little longer than you might think because of the square root, but the larger n is, the more you're dividing by, and consequently the smaller this is. So there it is again. This thing measures the variability in the statistic x bar, and the larger the sample, the smaller the number that measures how much it varies. So we're back to the same place we were with the p-hat formulas, the same general observations. The mean formula tells you that there's no bias. The standard deviation formula tells you that large sample, less variability, which is what I'm saying in this paragraph. These rules say that x bar's randomness is centered in the obvious place, but it's much more likely to be close to that center for a larger n. So in other words, the average of so many repeats is bouncing around that original population center. But the more of them you average together, the more tightly around it it's bouncing. Like our target pictures. They were both centered in the proper place. Our unbiased target pictures. Here they are. Large samples, well, in each case, the logical center of the shots is right where you were aiming for in the first place, or picking from if you prefer. But larger samples, they're tightly clustered up. Smaller samples, they're not so clustered up. So large sample, less variability. So summary. Let x bar be the sample mean, the mean of a simple random sample of size n from any population. I don't care what its shape is, but it's got mean mu and standard deviation sigma. The average of everything, the average of all the numbers out there, the standard deviation of all the numbers out there. Whether it's something you can compute in the case of all possible rolls of the die, or whether it's something that you're given at the start of the problem, as in the case of the heights of everybody in the world. Then the logical center of the sample mean's randomness is the center of the population you were picking from. The mean of the mean is the mean. And the logical spread of the sample mean's randomness, well, again, two things affect how the average of so many whatevers varies. the inherent variation in the whatevers, and how many are averaging together. Example, take the fair die. So for the fair die, remember, we did it in section 5. The mean was 3.5, and the standard deviation was about 1.708, rounded. So then if you're talking about the average of 100 rolls of the die, well, then the logical center of its randomness is still 3.5. 100 rolls of the die, in terms of what you're likely to get, is still bouncing around 3.5. But it's bouncing around 3.5 10 times closer. Two things affect how the average of 100 rolls of the die varies, how it's likely to be different from another average of 100 rolls of the die. The fact that you're talking about die rolls, how they vary, and the fact that there's 100 of them. So divide by the square root of 100, divide by 10. And all said and done, it would help if you did it properly. So there's a typo. That is 0.1708. And I am just quickly making a note of that. That's my own sloppiness. So dividing by 100, dividing by the square root of 100 is dividing by 10. It'll move the decimal once. So it's properly done. It's 0.1708. Sorry about that. It's correct down here. Well, more or less. That's a 0. So instead of varying on the order of 1.7-ish, it's varying on the order of 0.17-ish. It's bouncing around that 3, that's right anyway. It's bouncing around the 3.5, but on average, it's 10 times closer. The average of 100 rolls of the die is 10 times more likely to be close to 3.5 than the average of a single roll of the die. And so on and so on and so on. Average of 10,000 rolls of a die, and we still have some cut and paste errors, but it's getting a little better. Or not, actually. So let's do it verbally correctly here. The average of 10,000 rolls of a die, well, it's still bouncing around 3.5. But the square root of 10,000 is 100, so we're going to move the decimal twice. It would be this guy anyway. Move the decimal twice. There, there. So 0.01708. So more or less like this, but with a 0. 0.01708. In other words, this is 100 anyway. So you're still bouncing around 3.5, but on average you're 100 times closer. 10 times than the previous one. So if you're bouncing around 3.5 and you tend to be properly done 0.01 something away from it, you don't tend to be very far from 3.5. We'll put it together as we go on, but that's the basic idea. Remember, this is only the law of large numbers with a little math behind it. The average of what you do pick, as you pick more and more and more, you never get close to taking a bite out of what you're picking from. But as you pick more and more and more, the average of what you do pick gets very close to the average of what you could pick. The average of many rolls of the die will probably be very close to 3.5. So all the standard deviation does is put a little math behind how close. So let's look at some examples of how this plays out. Let's look at the die roll example. And you can maybe, oh, by the way, once again, let me make the point that it is one thing to be able to compute the mean and standard deviation of a statistic, and it is another thing for the mean and standard deviation of the statistic to be useful, to be something you can compute with. When has the standard deviation of anything ever been useful? When we're doing our normal procedures. So you can maybe see how all this is going to come together, but just in case you can't, here is how it works out for die rolls. Now, I should point out, this is not ideal. These are simulated on Excel with something like 30,000 die rolls, and doing what I was trying to do here was kind of pushing the limits of Excel, so it's not going to be perfect. And Excel's random generator, Excel's random number generator is less than perfect, so there are going to be irregularities here. And ultimately, I am talking about 30,000 samples, 30,000 die rolls, not all possible die rolls. So there's still going to be a teeny bit of randomness in the equation, but I'm simulating all possible rolls of the die here, for instance. And I'll show you how this plays out. So what I've done here is I've used Excel to generate thousands of rolls. I think it was like 30,000 rolls of a fair die. That is simulating all possible rolls. So, and then I've just made a histogram of the data that resulted. And the histogram program is less than perfect here, but of course this is the bar for 1, bar for 2, bar for 3, bar for 4, bar for 5, bar for 6. So this is my simulation of, shall we say, the average of all possible die rolls. Do a roll of the die, what do you get? Let me say that again. Roll the die, what do you get? In other words, a sample of size 1. Now let me point out that dividing by the square root of 1 is not changing your answer in any way, but here we are. So our pattern of randomness is bouncing around. Remember, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So our pattern of randomness is obviously centered directly here at 3.5. And you could at least buy that on average you tend to be 1.7-ish to either side, right? So nothing particularly new there. We talked about it since section 5. The only difference now is that I'm thinking of a die roll as an average of 1 die roll, a bit sarcastically. How does the picture change when I do the average of 2 die rolls? Now again, this is 30,000 averages of 2 die rolls. But what I'm doing is I'm simulating, that's about as far as Excel would go without erroring out. I'm simulating all possible die rolls. So here's my simulation of all possible averages of 2 rolls. So I've rolled 2 dice 30,000 times, added them up, divide by 2 to get 30,000 averages of 2 die rolls. So this is my simulation of all possible samples of 2 die rolls, what they average up to. And you can see it. It still centers at, 1 plus 1 divided by 2, 6 plus 6 divided by 2. So 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, 6. Now if we did it for sum rather than average, it would just be 2 to 11, right? But I divide by 2. So 1, 1.5, 5.5, 6. 3.5, right? I've still got that perfect symmetry. And it's centered around 3.5 still. The average of 2 die rolls in terms of what it's likely to be. Remember, you can think of this picture as representing how all possible averages of 2 rolls break down, or you can think of it as representing what the average of 2 die rolls is likely to be. This is 1/36th of the area. So 1/36th of the time, 1/36th of all possible averages of 2 rolls give you an average of 1. 1 plus 1 divided by 2, 6 times a sixth. Alternately, there's a 1/36th chance that the average of 2 die rolls will result in a 1, right? All possible averages of 2 rolls, pattern of randomness 4, the average of 2 rolls you're about to do. As always, the one is exactly what we mean by the other. So think of it as the pattern of randomness, simulation of the pattern of randomness for the average of 2 rolls. You're still bouncing around 3.5, but look at the area. On average, you tend to be closer to 3.5. Well, by a factor of square root of 2. The mean of this x bar is still going to be 3.5, but the standard deviation is now 1.708 over the square root of 2. Well, something smaller than 1.708. And you can see that the variability, on average, you tend to be closer to 3.5. Crank it up to samples of size 3. I've got my curly quote error things here. You can go to Western encoding or just not let it bother you. But samples of size 3. Now again, my histogram program is less than ideal, and we are talking about 30,000 averages of 3 rolls, not all possible averages of 3 rolls. So it's less than perfect, but this is something of what it looks like. So here's my simulation of all possible averages of 3 rolls of the die. And you can see more or less, it's not perfect because it's a finite number of averages ultimately, but you can see that it is still bouncing around, it's still centered at 3.5, but compared to what we had going on previously, there's a lot more area close to 3.5, and there's a lot less area further away. So the standard deviation of X bar, the average of 3 rolls, the standard deviation of the average of 3 rolls is even smaller. The thing that measures how far away from that still 3.5 you're likely to be is a smaller number. Samples of size 4. Now again, don't let the width of the bars bother you. At some point, the program I'm using to make the histogram just can't deal with as many bars as I would ideally like. But at some point, of course, probably around here, the bars stop representing individual possibilities and start representing ranges of possibilities. So don't let the number of bars affect this conversation. The number of bars is just a limitation on my ability to get decent pictures, and it's a reflection of the fact that I'm not really doing all possible averages, only 30,000 of them. So, but nevertheless, look at the shape. Think what has to happen to get an average of 1 roll of the die being 1. Well, it happens a sixth of the time. Think of what has to happen to get an average of 2 rolls of the die being 1. 1 plus 1 divided by 2, a sixth times a sixth. Think what has to happen for the average of 3 rolls to be 1. 1 plus 1 plus 1 divided by 3. A sixth times a sixth times a sixth. 1 over 216. Think what has to happen for the, now again, the bars start to represent more than one possibility here, but think of what has to happen for the average of 4 rolls to be exactly 1, that first thing you can be. 1 plus 1 plus 1 plus 1 divided by 4. A sixth times a sixth times a sixth times a sixth. 1 over 1296. You can see that the outlying possibilities are becoming very, very unlikely. So you can see the area gravitating inward, right? You're still bouncing around 3.5. It's still where you're centered, I mean, ideally. But the thing that measures how far away from 3.5 you're likely to be, the standard deviation of X bar, the average of 4 rolls, that guy is going down and down and down. I mean, look at it. Don't look at the number of bars. Look at the general trend of the area. You can see it gravitating inward. There's still a fair amount of area over here, but it's beginning to dry up, right? So the thing that measures how far away from 3.5 you're likely to be, the standard deviation of the statistic, is going down and down and down. And so on and so on. Now I should point out, if these sample sizes are beginning to worry you, I should point out that this is not an exact science. When you are trying to select and copy so many columns and so many rows and 30,000 columns, or the other way around, on Excel, it's not an exact science. You basically have to select what you manage to select. So that's why you've got these weird sample sizes. But look at the trend. Samples of size 5, still bouncing around 3.5, but the probability is gravitating inward. The standard deviation of the statistic, the spread, is going down. Samples of size 6. Again, it's not about how many bars we're using. That's the vagaries of the histogram program. But note the general trend of the probability. It's coming in and in and in. And by the way, is the shape starting to look familiar? Samples of size 10. Think what has to happen now to get an average of exactly 1. You need to get 10 ones in a row. A 6 times a 6 times a 6 times a 6 times a 6, just for giggles. 1 over 60466,176. What is that? Uh, about 60 million. 1 over about 60 million. Highly unlikely the average is going to be exactly 1. So much so that it doesn't look like it even happens in 30,000 examples. So, average of 13 rolls. Again, still bouncing around 3.5. And by the way, notice these are not on the same scale. If I overlaid them with one another, you'd see it getting taller and thinner around 3.5. Now we're only going from 2 to 5 on a good day. Other than that, it doesn't look like it happens virtually at all. Samples of size 31. Well, now anything less than 2.5 or more than 4.5 is beyond the pale. Again, if you superimpose these, you'll see taller, and we're tinkering with our scale here, right? But if you superimpose these, you're going to see taller and thinner bells around 3.5. So still bouncing around 3.5, but on average, you tend to be closer and closer and closer. The standard deviation, the spread, the variability is going down and down and down. Samples of size 51. They're all online. You can check them out at your leisure. Samples of size 73. A very, very tall, thin bell around 3.5. I mean, this is 3 and this is 4. The average of 73 rolls being less than 3 seems to be almost beyond the pale, and likewise more than 4. Samples of average of 167 rolls of the die. Now being less than 3.2 or more than 3.8 is kind of beyond the pale. Much less variability, smaller and smaller standard deviation. Superimpose them, taller and thinner bells around 3.5. Average of 301 rolls, well, still centered at 3.5, but now you can see that it's even, on average, or even closer. Anything less than 3.2 or 3.8 is now virtually impossible, right? Average of, call it 500, 497 rolls, still centered at 3.5, but now less than 3.3 or more than 3.7 is almost beyond the pale, right? Average of 1200-ish, 1227 rolls, now being less than 3.4 or more than 3.6 is almost beyond the pale. Average of 20,000 rolls, 2076. And you can see it again, a much, much taller, thinner bell. Well, number one, the area is coming in and in and in, right? The area, picture to picture to picture, the area is gravitating inward, which is shrinking the spread, which is making smaller the number that measures the spread, standard deviation. This is the point at which Excel begins to implode, and the comments I just mentioned here you can read about. So, number one, the area is gravitating inward. Number two, compared to our original up top, right? The area is gravitating inward as I average more and more and more rolls together. But number two, as the area gravitates inward, the natural consequence of that is a familiar shape begins to emerge. More on that a bit later. Okay, the die roll example is a rectangle. It's reasonably symmetric. Maybe that's not all that weird. Okay, let's take an example that is very weird. So on the planet Centauri Prime, there's 3 times as many females as males. Polygamy is mandatory. Twin births are commonplace. This is just all by way of putting some real-world spin on the following probability distribution, which is completely cockeyed and about as weird as I could think of making it. So, all adult males at 18 must marry twins, and they are allowed 1 additional wife. So, how does this work out? The number of wives of a citizen of Centauri Prime. Half the population are women and have 0 wives. 1/3 of the men have married twins and have 2 wives. The rest of the men have 3 wives. So, here is how that breaks down. If you look at the population of Centauri Prime, there's a 1/2 chance that they have 0 wives, or 1/2 of them do. There's a 1/3 chance that they have 3 wives, and there's a 1/6 chance that they have 2 wives. I may have said that backwards, but you get the idea. I'm pretty sure I said this bit backwards, but anyway, here you go. So 1/2 of them have 0 wives, 1/6 of them have 2 wives, a third of them have 3 wives. So totally asymmetric, totally weird. What's going to happen as we look at more and more averages from this population? Well, first of all, because of what populations and randomness is, if you pick somebody at random, there's a 1/2 chance that they have 0 wives, and a 1/6 chance that they have 2, and a 1/3 chance that they have 3. So if we look at the curly quotes is not coming up well with this. You go to Western encoding if it's really going to bother you. Oh, by the way, from section 5, 0 times 1/2 plus 2 times a 1/6 plus 3 times a 1/3 is 4/3, 1.3 repeating. So the average Centauri has 1.3 wives. So the logical center, the physical balance point of this, if it were a sheet of metal, is right there at 1.3. It's just the way it balances. The average of all possible. Everybody on the planet average their number of wives together. 1.3 repeating. 4/3. That's the logical mean. Likewise, the standard deviation is 1.374 for what it's worth. And again, from section 5. Now, if we average together 2 repeats from this population, it starts to look like this. It's still bouncing around 1.3 repeating, which is here-ish, but look where the area is going. Now again, the averages here can only be so many different numbers, right? 0 plus 0 divided by 2, 0 plus 2 divided by 2, 0 plus 3 divided by 2, 2 plus 3 divided by 2, 2 plus 2 divided by 2, 3 plus 3 divided by 2. So there aren't a lot of different things you can get when you average 2 of them together, but here they are. And you can see that even when you're talking about the average of 2 repeats, already the probability is tending to gravitate inward. It's still bouncing around 1.3 repeating, 4/3. But now you tend to be a little closer. Average of 3 repeats. Still balancing at 1.3 repeating, but now the spread is going down, right? It's less spread out. The area tends to be a little closer to 1.3 repeating. All of these are centered in the exact same place where my cursor is here, but the area is coming in. The standard deviation, the thing that measures the spread, is going down. Still some interesting peaks and valleys, but it is coming in. Samples of size 4, well, still some interesting peaks and valleys, but still centered around 1.3 repeating. It's a teeny bit right skewed, I would say here, maybe. Still centered at 1.3 repeating. That's going to screw with your intuitions of balance, of course. But still centered at 1.3 repeating. Some interesting peaks and valleys. But note the area coming in and in and in. Samples of size 5, well, the gap in the middle is a little weird. It comes and goes if you change the number of bars and so forth. Still centered around 1.3, but the area is gravitating inward. Samples of size 6, still centered around 1.3, but the area is gravitating inward. Let's jump ahead to samples of size 20, and that's enough to make the point, right? Still centered around 1.3 repeating, but beginning to take on the bell shape. Even though we started with the weirdest shape we could imagine. Not symmetric, nothing remotely symmetric about it. Still we get back to the bell shape. Samples of size 40. Notice here they generally trend from about 0.5 to 2.5. Here they're trending from about 0.7-ish to 2-ish, so you can see it coming in and in and in. Superimpose them, and you've got taller and thinner bells around, well, taller and thinner patterns, which are looking more and more like bells, centered around 1.3 repeating. Samples of size 80, again, they're not superimposed, but you can see that the ends are coming in. You're probably not going to have an average of 80 being less than 1 or more than 1.8. Average samples of 120, samples of 240, samples of 480, samples of 600, samples of 1200. Definitely looking more and more like our normal distribution. Remember, in the end, it's a finite number of repeats on Excel, so it's not perfect. But definitely looking more and more like our normal distribution, pretty clearly centered around 1.3 repeating or thereabouts. And taller and thinner bells, even 1.2 or 1.5 is kind of beyond the pale now. Samples of size 2,000, even 1 1/4 or 1.45 are now kind of beyond the pale. Samples of size 4,000, well, you can see it's getting taller and taller and thinner around 1.3 repeating. The average distance from the center is going down and down and down. And that's about as far as that would go before erroring out, at least when I did this. So put it all together and you can see where this is going. I'll correct those typos, but this was 0.1708 and this was 0.01708. So in the end, we know two things. We know that when you combine normal shaped things, it's still normal. So the average of so many repeats from a normal population is still going to be normal. But on the other hand, neither of these examples we just did were normal, right? The one population was 6 bars all the same height, not very bell-shaped, and the other was 3 bars of varying heights, also not very normal-shaped. But nevertheless, it trended back to the normal shape in the long run. So I'll explain how all this plays out in the next video, but it's just another example of what we did in Section 8. Whenever you combine many repeat performances into a single variable, the resulting variable ends up being normal shaped, or it gets closer and closer to normal shaped. We saw it for the proportion of yeses, and now we're seeing it for the average of so many numbers. So I'll pick that up in part 2 of this video.